Today we're going to talk about 8-1, similarity in right triangles. Let's first start with the definition of geometric mean. You may have heard this before, but it's a positive square root of the product of two numbers. So in other words, that could be confusing just reading. So the geometric mean of two numbers, let's say a and b, x is equal to the square root of a and b, or simply x squared is equal to ab. So for example, let's find the geometric mean of 4 and 25. We know that x squared, I want to use this second half of it because it's fairly easy from there. X squared is equal to 4 times 25. So we know that x squared is equal to 100. Well, now we want to know what x squared is, or rather we want to know what x is. So we take the square root of both sides, which gives us x on the left-hand side and on the right-hand side. Now, yes, we add in a plus or minus, but because by definition a geometric mean is the positive square root, we don't actually need the plus or minus. So therefore, we know it's going to be the positive, and the square root of 100 is 10. So our answer is positive 10. Now, before we apply the geometric mean, we need to introduce a theorem, which is 8-1-1. The altitude, as a reminder what an altitude is it's a line perpendicular to another line. So the altitude to the hypotenuse of a right triangle forms two triangles that are similar to each other and the original triangle. So, for example, let's just say, well, we have a right triangle. Now let's call this right triangle triangle A, B, and C. Now we want, let's see, the altitude to the hypotenuse of a right triangle. So we're looking for a perpendicular line to the hypotenuse. Remember, the hypotenuse is the longest side, and we're looking for a line perpendicular to it. So let's go ahead and draw on a line. Looks like it would be about this one, would be perpendicular. And let's call this point X. What this theorem tells us is that it forms two triangles. Well, it did. It formed AXB and it formed CXB. So it formed two triangles, but these two triangles are similar to each other. So this is the whole point of the theorem, is that triangle AXB is similar to triangle CXB, and both are similar to triangle ABC. And that's that last part of the theorem, is that they are similar to the original triangle. So it's actually kind of a nifty theorem. A little proof of it would involve dealing with angle, being that you have an angle from the original and then you have another, which is the 90 degree. And then you use the transitive property to prove the last part of it. It's actually quite a cool theorem and very useful, as you'll see in just a second. So our first corollary that deals with the geometric mean is corollary 8-1-2, says the length of the altitude, which we just talked about this, to the hypotenuse of a right triangle is the geometric mean of the lengths of the two segments of the hypotenuse. So again, if we had a triangle similar to before, where we have this right triangle, let's go ahead and call it A, B, and C. Now we're looking at the altitude to the hypotenuse. So we're looking at this line again. And now I want to know, how long is XB? I want to know what is the length of XB? Well, hey, the length of the altitude to the hypotenuse, which is XB, is the geometric mean of the lengths of the two segments of the hypotenuse. So it is whatever the geometric mean of AX and XC. So we know that XB, whatever this actual length is, squared, is simply equal to the length of AX times XC. Nothing too crazy there. Now we have a very similar corollary here. It says that now if we're looking for the length of a leg of a right triangle, so maybe if we're looking for AB or BC, the length of a leg of a right triangle is the geometric mean of the lengths of the hypotenuse, so whatever that hypotenuse is, and the segment of the hypotenuse adjacent to that leg. So for example, if let's say we want to know how long is AB. So this length right here, what's that distance? Well, the length of a leg of a right triangle is the geometric mean. So we know that whatever that length is squared is equal to the length of the hypotenuse. So whatever the hypotenuse is, which is AC, times the segment of the hypotenuse that's adjacent. So we're looking for AB. So we're either going to consider AX or CX. But since AB is right next to AX, that's the one we want to look at. And this is what our corollary tells us. Let's go ahead and do a quick example dealing with those two corollaries. So we want to find X, Y, and Z. Let's go ahead and start with X. Trying to find X. Well, what I notice in this is that I have a right triangle. So I also have a right triangle, and I have this, I see a right angle right here, meaning this line right here is that altitude to the hypotenuse. So I say, well, let's use that first corollary we talked about, which was 8-1-2. What this says is that this length is the geometric mean of 9 and x. So meaning that 6 squared is equal to 9 times x. Well, now we just simplify. 6 squared is 36. 9 times x is x. Solve for x. We divide by 9, and we see that x is equal to 4. Nothing too crazy, just corollary 8-1-2. Now let's go ahead and look for y. Well, for y, I realize it's the leg of a right triangle. So to find the leg of a right triangle, I'm going to use corollary 8-1-3. And that says that it's the geometric mean, so I'm going to have y squared is going to be the length of the hypotenuse. Well, if x was 4, then we know the overall length is 9 plus 4, or 13. So it's going to be 13, the length of the hypotenuse, and the adjacent segment, which is going to be 4. So 13 times 4. So y squared, you can type that in a calculator if you need to, but it's going to be 52. And now just solve for y. You take that square root, and again, we don't put plus or minus just because we know the answer is going to be positive. So y is equal to, now we need to simplify this square root of 52. To do this, we say what numbers can we take out of 52 that have a square root? For example, do you know the square root of 2? No. Do you know the square root of 3? No. Do you know the square root of 4? Yes, you do. So the square root of 52 is the same as 4 times 13. But since you know the square root of 4, the 4 comes out. Now when it comes out, whenever it goes underneath, you have to actually take the square root of it. So the actual square root of 4 is 2. So 2 square root of 3, 13. And now you check the number 13, but you know it's prime. And so therefore y is simply equal to 2 square root of 3, 13. Now we move on to z. Again, I see it's a leg of a right triangle, so we're going to use corollary 8-1-3. Very similarly, I know that z squared is going to be equal to, again, 13, but now times 9. So z squared is going to be equal to 117. Take the square root now. Z is equal to the square root of 117. Now you need to simplify. Remember, you're pulling out numbers that you know the square root of. So you know the square root of, not 2, not 3, but you know the square root of 4. Does 4 go into 117? No, it does not. So you also know the square root of 9. Does 9 go into 117? Well, obviously. So 9 goes into the square root of 117. So this is the same as square root of 9 times 113. But since you know the square root of 9, the 9 comes out. Take the square root of that now, which is 3 square root of 13. I noticed that I made a mistake right here because it should have just been 13 instead of 113. So anyway, z now is 3 square root of 13. Now we've used the geometric mean and our two theorems, or rather our theorem, which led to our corollaries, to find all of these side lengths, which were not possible before. So incredibly useful theorems here. Write down any questions you have, and I hope all this made sense to you.